Hello everyone, this is Neha Sisodia, Assistant Professor at New LG Institute of Engineering and Technology. We are going to discuss query processing and optimization. Query processing and optimization are part of our fifth unit, and we are going to discuss about some join strategies in query processing. So what this join operation we have in our query processing, we have several different algorithms that implements join: nested loop join, block nested loop join, index nested loop join. We have choice based on cost estimated. We are using one example in which the number of records of a relation customer and relation depositor are 10,000 and 5,000 respectively, and the number of blocks of customer are 400 and depositor is 100. So let's take an example. This is the running example where we have two relations. There is depositor and customer. We have joined it together. So the catalog information for join is the number of records are 10,000, and for depositor it is 5,000. We have block size of 50 and 25 for depositor and customer, and we have also seen the number of blocks are 400 for customer and 100 for depositor. So we have a join with customer name and depositor that will have 2500. So which implies that on an average each customer has two accounts. So let's assume that the customer name is in depositor and is a foreign key for customer. So estimation of the size of join will be from the number of tuples we have. So the Cartesian product of R and S, we have two relation R and S, let's suppose, and it will contain NR and NS number of tuples. So each tuple actually occupies space SR plus SS bytes on disk. So if we have nothing in common with the relation R and S, that is the intersection of both the sets are phi, then we have R and S will be same as R cross S, because we are going to join each and every row, every tuple with the another one. If the intersection is a key for R, then the tuple of S will join with at most one tuple from R. So the number of tuples in R and S are not greater than the number of tuples in S. So if the intersection of S is a foreign key in S, which is referring R, then the number of tuples in the join of R and S is exactly the same as the number of tuples in S. So the case for R and S, the intersection of R and S being a foreign key referencing S is actually symmetric. So in this example, the query that is depositor and join over customer, the customer name in the depositor is serving as a foreign key for customer. So the result is exactly number of depositor tuples, which is 5,000. Similarly, if R and S is having a common attribute A, so is not a key either in R or in S, in both the tuples, if it is not serving as a key, what we do is, if we assume that every tuple T in R produces a tuple in the join of R and S, so the number of tuples in R and S is estimated to be the number of tuples in R and the number of tuples in S over the cross product of A and S. So if the reverse is true, the estimate obtained will be product of these number of tuples and the product of this attribute and the relation. So lower of these two estimates is probably more accurate one. So what we need to compute as the size of the estimator is, suppose we have a depositor and the customer without using any information about the foreign key. So we have the customer name and the depositor. We have 2500 tuples, and for customer name and customer we have 10,000. From customer we have 10,000 rows. So two estimates are 5,000 into 10,000, 5,000 from depositor and 10,000 from customer, by 2,500 minus 20,000. So, and another one is 5,000 into 10,000 upon 10,000, that is 5,000. So, this is how we are going to estimate the size of the join we have made. So, we choose the lower estimate, which in this case is the same as our earlier computation using the foreign key. So, size estimation for other operations, if we see like projection, the estimated size of projection of A from R is the product of A and R, and the aggregation estimation of size of this is always A aggregation of F, and this will also be the same. So, the set operations for union or intersection of selection on the same relation, we have to rewrite and use the size of estimate of the selections. For an example, suppose we have a theta condition for selection from R, and we have another condition which have selection from R itself, and we have to take a union of this. So, that can be rewritten as we have two different conditions from the same relation. We can have a subsequent serial conditions of this theta 1 and theta 2 over R. So, for an operation on different relationship, if we have to estimate the size of R union S, the size of R, summation of size of R and size of S will be the estimated size. Similarly, if we have the estimation of intersection of two relationship, that will give the minimum size of R and size of S. So, the estimated size of R minus S will be R, and all the three estimates, as we have seen, may be quite inaccurate, but it provides an upper bound of the size. So, that will be more closer to what will be the exact size. In the outer join, the estimated size of R outer join S, the size of R into S, that is the join of R and S plus the size of R, will be the estimated size. So, the case of right outer join is symmetric as well. If we have the estimated size of full join, that is R and S, we will have the size of join of R and S plus the size of R plus the size of S individually. So, estimation of number of distinct values, if we need to have a selection over theta of R. So, if theta forces A to take a specified value, that is, if we have a selection over theta and R with an attribute A, we will have a specific value that will give a value of an attribute A to be 3. If theta forces A to take one of the specified set of values, we will take a set of values A is equal to this, A is equal to this, or A is equal to this. So, any of the values will be taken off. So, if the selection condition theta is of the form A, operation A, so the estimation is going to be A dot R and the attribute from R, and we will get the product of S. So, where S is actually selectivity of selection. So, in all the other cases, we use approximate estimate of minimum of this and the number of tuples that we have selected by using the condition theta over R. So, more accurate estimate can be got by using the probability theory, which is beyond the syllabus. So, join of R and S, if all the attributes of A are of form R, we have an estimate of the attribute A with the join of R and S and minimum of the number of tuples of the join R and S and the attribute R and A. So, if A contains the attribute A1 from R and A2 from S, then we have estimated that the minimum value of A1R and A2 minus A1, that is all the values has to be subtracted from A2 from the S, and we also have to take the similar cost for A1 minus A2 comma R, that is all the values subtracted from A1 in the relation R, and we also have to take the product of A to S. And also we have to take all the tuples that are in join of R and S. So definitely we can got it more accurate using the probability theory that is beyond the scope of our syllabus. So estimation of distinct values are actually straightforward for projection. So they are exactly same as we do a projection of a particular attribute from a relation R. That same holds for grouping of attributes of aggregation, and also for some aggregated value like minimum of A, maximum of A. There are number of distinct value that can be estimated using this minimum. And for aggregate value, we assume that all the values are distinct, and we also use an attribute from a particular relation. We are going to discuss more on joint strategy in our next subsequent video. Thanks for watching.